Okay, I guess we can start to get started. First of all, any questions about anything, let's say logistical? Anything when the homework's due or anything like that? Okay, any questions about the programming assignment? Let's start to think. We have the backtracking assignment. We've talked about backtracking. I'm hoping to move on during today's lecture, but I do want us to go through it a little bit more just to make sure people get started. Is there anybody who started working on the backtracking assignment? A few people. Do any people have programs that run? Okay, let's look at several people have programs that run. Who can do the examples of 10 vertices if you've got programs that can run? Confident hands. Who can do 20 vertices? No confident hand. One confident hand still. Okay. What? Yes, yes. I mean, we want to know not in geological time. In the minute you're allowed to use it on your computer. So we got a bunch who can do 10. Who can do 20? One person claims to be able to do 20. Can anybody do 30? Okay, no one can do 30. Okay, so this is evidence that the problem. And how many lines long is your program?
About 250.
250. 300. 300. Okay, these still sound long to me, but that nonetheless, the fact that they exist compared to the other one, the shorter ones that don't exist, is very good. Okay, any questions about that? Okay, about the what we're trying to do. I think they will get faster with time. Okay, because I think we can probably make it do better. Any questions about the backtracking assignment? Is there anybody who wants to ask me a question like, I want another example of what bandwidth is, because I don't know what the thing we're trying to compute is. There were some people who were confused with this. Yes? Okay. How do you compute the bandwidth? Okay. What I want to say is, I'm going to separate two different things. There's calculate and compute. Okay. By calculate, it means if I give you a the bandwidth is going to be defined of the bandwidth of a graph is defined as the longest edge in the permutation that gives you the shortest edges. Okay, let me try to say that one more time. Okay, so if we take a look at a graph, let's see if we can construct an interesting graph. Let's say a grid. I haven't tried this one yet. Maybe this is going to be too complicated to do. Let's say our graph is a grid on two levels. Okay? And this is going to be, the vertices will be numbered 1, 2, 3, 4, 5, 6, 7, and 8. Okay? Now, the bandwidth of the graph is going to be defined by the permutation that when we draw it has the shortest long edge. Okay? So what permutation of the vertices could we use? We could use the permutation 1, 2, 3, 4, 5, 6, 7, 8. If we write the vertices in that order, what is the longest edge that we end up getting? I think there is an edge that goes from 1 to 5 and from 2 to 6. These are the longest edges in that drawing. Does everybody see that? Is there a better drawing for this one? Okay, where the edges won't be quite as long. Okay, yeah.
1, 5, 2, 6, 3, 7, 4, 8.
So you want to say another possible drawing would be 1, 5, 2, 6, 3, 7, turn it in, okay, 3, 7, 4, 8. Okay, what's good about this drawing is the cross edges are clearly going to be short. Does everybody see that this permutation? But are all the edges short? Okay, I see that I need an edge from 1 to 2. That's short. From so this vertex from 2 to 3. Okay, my handwriting is going to start to get too complicated for me, but it looks like to me. Let's look at the other ones. 6 to 7, it does look to me like this does not span more than 2 edges. Do we agree with that? Let's try that. Let's write that more neatly to see if we really believe this. 1, 5, 2, 6, 3, 7, 4, 8. Does everybody see that's the order of the vertices? This graph here has 3 top edges, 3 bottom edges, and 4 cross edges. With this drawing, the cross edges, ka-chunk, 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 are all of length 1. The top edges, 1 to 2, 2 to 3, and 3 to 4, are all of length 2. The bottom edges, okay, which go from 5 to 6, 6 to 7, and 7 to 8, are all of length 2. This is a better drawing. This is a drawing of length 2, okay, bandwidth 2, whereas this one was a drawing of bandwidth 4. Does everybody see that? Okay, was it yeah, I think we would call it 1, 2, 3, 4. Okay? How do we know there's not a drawing of length 1 for this graph? Yeah? Is it true that if we have a node of length of 2 edges, that the bandwidth has to be of at least 2? No. Okay, what about this one? Ka-chunk and ka-chunk. Here we've got a node of degree 2, okay, and yet the bandwidth is 1. Okay, yeah?
There are at least 2 nodes of degree 2.
You say at least 2 nodes of degree 2? I don't believe that either. Look, I can have a disconnected graph. Ka-chunk and ka-chunk. Okay? So that's not quite a condition I need. Yes?
There is a node of degree 3.
Now, a node of degree 3 is interesting. What does a node of degree 3 tell us? The bandwidth has to be at least 2. Does everybody agree with that? Because you can't pack enough vertices near close by vertices near the center of that high degree node. So this might provide some idea to help limit your search, okay, or to give you some ideas as to how well you can hope to do. Okay, yes? How does the edge from 1 to 5, you mean, wait, on this graph?
Yeah.
There is an edge from 1 to 5. This is an ordering, see how we've got the permutation of the vertices. This red thing is a permutation of the vertices. Okay? Here, 1 and 5 are neighbors of each other. Okay? So this edge from 1 to 5 is really only a short edge. See how short that line is? See, when I drew the graph down here, if I drew the graph down here, this was a long edge. Okay? But with this arrangement of the vertices, all the edges are short. That's the important thing to see here. With this arrangement of the vertices, all the edges are no more than length 2, whereas on this one, there were edges of length 4. If our goal is to make the longest edge as short as possible, this is a winning solution. There might be other winning solutions, but we've argued there can't be a better one. So I don't have to search anymore once this is found. Okay, any questions? Yes?
So is the three edges, is that the rule, or is it that there has to be, or is it because there are 2 edges for every one?
Well, I'm not going to tell you now. Okay, well, let's look at this. A degree 3 vertex. Let's look at the very simple case. Is it possible, if you have a graph with a degree 3 vertex, for there to be no edge longer than 1? Okay? And the answer is no, because we're saying, what do you mean? I can have 1 here, I got 1, that's of the edge length 1. Here I got another one, that's of edge 1. But you got a third edge and you got to put it someplace, right? And wherever you put it, it's got to be at least 2 away, right? So there is a connection between the largest degree of the graph and the bandwidth, okay? Or at least a lower bound on the bandwidth. Okay? Any questions here? And again, efficient pruning means looking to see when a search can't help you. Okay? If I have found a solution that is as good as is possible, I don't need to look anymore. That's what I want to stop looking. Okay? Any questions here? Any other questions about the problem? How you go about doing it? Any questions about this problem? Okay? Again, so what could you do to solve it? You could construct all n factorial permutations using backtracking exactly like I did. Then once you got a permutation, you can check every one of your edges against that permutation to see what was the longest one. That would be n factorial permutations times m, because you have to compare every edge. Okay? Now, if you are smarter, however, you can avoid looking at all n factorial permutations. Okay? And that is the key idea here. Okay? Any questions about that? Okay? Yes?
If there are more than one best ones, do we have to print them all out or just one?
If there's more than one solution, I only want to see one. Okay? If you have to print out all the best possible solutions, you are doomed in certain examples to spending n factorial time. Right? So I only want one solution. Okay? But I want to know that there is no better solution than the one you're giving me. Okay? Any questions? Yes?
So based on this trick for figuring out the bandwidth, would it mean that a node of degree 5 means there must be at least 3 bandwidth?
You're saying that if there is a node of degree 5 in the graph, ka-chunk, how's the tightest I can possibly back those edges? Ka-chunk, ka-chunk. It certainly looks like there has to be a bandwidth of at least 3 there. Okay? That's the same argument. Okay? And there is probably a way to generalize this. Okay? For arbitrary degree. If the degree is D, what do you know about the bandwidth? Okay? Yeah? Rhetorical question. Okay? But hopefully some of you know, can now glean something. Okay? Any questions here? And that should help you reduce your search. Okay? Because once you know that there is no solution better than something, okay? If you have a solution that good, you can immediately walk away. Okay? Any questions here? Yes?
So we have to do this by permuting it rather than just trying to generate it.
You say you have to do it by permuting it rather than trying to generate it. No, what you have to do is do it by backtracking. So you're building up solutions, building up permutations, because the answer is obviously going to be a permutation. But whenever you have a partial permutation that you can prove will not lead to a better solution than you have already, that is when you should say, I have no candidates for the next slot. Right? If I have a solution of size 10, a bandwidth 10, and so far you've put down an edge of length 11, nothing you do to add to this permutation is going to make it any better. You should give up and not try any permutation that expands on what you've already done. Okay? That's what I mean by pruning, is recognizing when what you have done is a dead end. It will not lead you to a better solution than you have already found. Okay? Or than could possibly exist. Okay? And the quicker you realize that you're going down a bad, a path that can't possibly improve you, that's immediately when you want to backtrack. Okay? And so the pruning criteria is to try to look and analyze what you've got, your situation is, to see if there is any hope of getting better. Okay? If there is no hope, retreat. Okay? Or backtrack. Any questions about this? Yes?
How deep into the group theory should we get?
You're allowed to get into as much group theory as you want to get into. And so if you know about group theory and you know what you want to do, that's fine. there's no magic that I think is going on here. Okay, so I mean, group theory is sort of an algebra about symmetry and a lot of other properties of things. But basically, there's different ways of looking at this thing. And so if you guys are not here understanding what he means by group theory, don't worry about it. I don't think that is necessarily a win here. Okay? Any questions here? But what is a win? You don't want to look at anything more that can't possibly lead to a better solution. Symmetry. If you already have checked out one thing, you don't want to check out a reflection. Okay? The more you can prove, the better off you are. Any questions here? Okay, any other questions about the homework assignment or the program before we get going? Okay? Okay, good. Okay, so let's move on, but that is our initial goal. Okay, what I'd like to, let's actually, before we move on to away from backtracking for the day, today's problem of the day is about backtracking. And it has to do with constructing all permutations of a multiset. What is a multiset? A multiset is a set where elements, where you're allowed to have repeated elements. Okay? So in permutations, when we were talking about it, we sort of assumed that the elements were distinct. A permutation on n things was an arrangement of the numbers 1 through n. Sometimes we might be given a set of things that have repetitions and say, find me all distinct ways to order these things. That's what we mean by a permutation of a multiset. Note that here, if my elements are 1, 1, 2, 2, that you could say that's 4 elements. That would mean 4 factorial equals 24 permutations. But if you look at it, there are only 6 distinct arrangements of these elements because they are, because some of the elements are repeated. Does everybody see that? So my goal here is design an efficient algorithm for constructing all permutations of a multiset. Okay? If we have n elements in our multiset, what's the maximum possible permutations of that multiset? Yeah?
It's n factorial divided by a1.
If they are all distinct, it's n factorial. What if they are all the same? What if it's n copies of 1? How many different arrangements are there of that? Exactly 1. Okay? So there is a big difference if you efficiently generate, if you want all of these arrangements. The number of distinct arrangements of the multiset are far less than the number of just permutations of elements if the elements were distinct. Okay? So how do we go about generating these things? Okay? Yes? Can you offer your solution? Tell me about your solution. Let's.
Create an array. Basically, it's backtracking the same way.
Okay. Backtracking. That's what we want. Okay.
And you start off by just saying that anything can go in the first box, and then anything but that can go in the second. And then through backtracking on the way back, you just make sure that you don't switch it out for a number. Actually, be sorted first too. You don't switch it out for a number that was already just in the box.
Okay. So what you're saying may or may not be right, okay? But I'm going to tell you I don't like to think of it that way because I like to think about, I like to limit my thinking to my particular backtracking implementation. I describe a backtracking solution in terms of 3 functions that I have implemented. Okay? Obviously you can write your own backtracking and do things, and that's why I say you may very well be right. But I am looking for a solution that is going to can be banged into my framework where the 3 things that I am doing are, I need to test, is my array, I need to come up with what my solution vector A is going to be. I need to know what my is a solution is. I need to know what construct candidates is going to do. Construct candidates. And then what process solution is going to do. Right? So now, can you tell me how you're going to do it in terms of these 3, or we want to try someone else? Okay, so first of all, what is the array representation going to be? Okay, let's try to think of it this way. What is my vector going to be? Okay, to represent the solution. Yeah? You're going to say it's going to be an array of n elements. And what are you going to put in each element? One of the k, okay, so one of the elements of the multiset. Is that right? Okay, so maybe the real input to this thing is going to be, let's say that I have elements 1 to k, and for each one I've got a certain number of copies of it, right? That's what the input to this problem really is, right? And in this particular case, I have got 2 copies of 1 and 2 copies of 2. Okay? Does everybody see that this is the input of my problem? Okay? Does that make sense? I'm getting a frown, so I'm not sure people are buying that. Okay? This is what I want to say. I'm going to describe my input. Okay? You're saying my output, my vector, is going to be an array where at each slot I'm going to have one of these elements. Okay? 1 to k, correct? Okay. Now, when is this thing going to be a solution? A final solution? So you want to say, if is k equal to n. That's what you're really saying. When I filled my array up, you've got a solution, right? What are my candidates for the kth spot, though? Okay, what are the possible candidates for the kth spot? Okay, yes?
All, if you iterate through your list of, you say you have 2 1s and 2 2s. If the candidates are all values that aren't equal to, that you don't have 0 of.
All elements that I don't have a 0 of. Okay? Does everybody see that what he's going to say is that I've got a particular prefix here? Okay? And what I'm going to do is I will have used in my prefix that I've put down a certain number of, in this case, 1s, a certain number of 2s. Okay? And you're going to be saying my candidates are going to be a 1 if I have still an unused 1, and a 2 if I have an unused 2. Does everybody see what he's saying here? Let's go back and look at an example. Suppose, let's say, I have already put down a 1 in my array. What are my possible candidates for the next position in the array? 1 or a 2. If I have put down a 2, a 1 again, what are my possible candidates for the next spot? Only 2. Okay? And if I put down a 2 here, I would have had either a 1 or a 2. Does everybody see that? Okay? And so basically what you're going to be doing here in construct candidates is count the number of elements in which elements I have used in the partial solution. Decrement the count of those things. The number of available copies of each one I have will be left there. And so long as the number of available elements is less than 0, there is a way to extend my current solution into a permutation of a multiset that contains that prefix. Okay? How many people see it? How many people don't see it? Okay, any questions about that? Yeah.
Would there be a way to check if in the array where you had 2 2s and 2 1s, if we have only one variable left, just fill up the rest of the array?
Okay, so you want to say, if there is, you want to say, what if, let's say, I am given a multiset of 1, 1 and 100 2s. Okay? And you're saying, what if I have put down a 1 already? Now I know I can fill in the whole thing. Should I get out of this backtracking stuff and just fill it in? Okay? That's really what your question is. And my instinct is to say no. Okay, and why is that? Because what is backtracking going to do naturally here? If you think about it, the candidates at each slot are always only going to be one candidate, right? There's only going to be 2s at each slot. So when you have a backtracking search where you've got only one possible candidate for that thing, it doesn't take much time to fill it in. There's nothing exponential about it. Okay? And it's really going to take constant time to fill in each cell just by going through the mechanics of backtracking. Okay? So I wouldn't write something special to handle that case. Okay? Does that make sense? Okay? So thinking in the, might say, aha, I can save a little bit. But it's really a weird special case. The important thing in backtracking is to avoid searching too many different copies. Okay? Filling on when you have only one branch to make, okay, it doesn't cost you anything to make it. Okay? When you have 2 branches, now you're in exponential turf. When you have one branch, it's linear. Okay? And you're not really going to beat linear by doing something special. Okay? That's my way of thinking. Any other questions about it? Any other questions about backtracking, how this worked, or anything like that? Okay? Again, there are ways you can write your own backtrack procedure, and you can do that will have a little bit more flexibility than my bang everything into is a solution, process candidates, and construct candidates. Okay? But in general, this is the way I think about things. Okay? And I think that as you're getting started, this is the right way to think about it. Okay? Any questions? Okay. Let me think if there's anything else here to talk about. Okay, let's just say, another way we could have done it, of course, is to just construct all permutations and then check in process solution if this is the first time we have seen it. Now that would be a terrible solution, right? Because it's going to take n factorial time to construct all possible things. And you are faced with the problem of recognizing whether or not you've seen this solution before. Okay? Much better is to actually prune at the time you construct, at the construct candidates phase, to make sure you don't construct anything you don't need. Any questions? Any more questions about backtracking one way or another? Chunk. Okay, good. Clear, chunk. Okay. So what I'd like to move on today is to a different area, in some ways very closely related idea, and in some ways a wildly different idea for algorithm design, called dynamic programming. And dynamic programming is one of my favorite things in life, okay? I mean, because it's a method for algorithm design that once you understand it is remarkably easy to apply, okay? Once you understand it. I work with various other algorithms professors on campus, like Professor Mitchell and Professor Bender. Occasionally we'll argue about a problem. Oh, how do we solve this algorithm problem? And we'll be deep in thought and we can't figure it out. One person will then say, dynamic programming. And everyone else will say, you're right. And that's the end of the discussion. Okay? Because once you see that for certain kinds of problems, it becomes kind of obvious once you've done this enough what the way to do this with dynamic programming is. That's not much of a help to you at the beginning because it takes a little bit of practice to see these things. But ultimately recognize that all the algorithms we're going to look at are essentially one-line recurrence relations. And once you get into that idea, you'll see somehow they can't be that complicated because the idea is simple enough to express in a short recurrence relation. That said, it looks like magic until you see enough examples. And so hopefully I'll show you guys enough examples over the next couple of lectures that it won't seem like magic. Any questions? So what is dynamic programming? Okay? It turns out to be it's a great way to solve optimization problems on things that have left to right orders to them. That's the way I think about them. What has a left to right order on something? Well, character strings have a left to right order on things, right? The characters here are all to the left of those characters, right? Permutations, certain problems on permutations. A permutation has a left to right order. It's stored like in a linear array. What other things have left to right orders on them? Turns out like binary trees, or trees if you lay them out in the plane. Does everybody see that the leaves here have a left to right order on them now? Right? What is it that we did with topological sort? Does everyone remember topological sort? What did topological sort do to a DAG? It ordered the vertices from left to right so that there was an interesting property to the edges. Okay? So these are the kind of things that for structures like those, things like dynamic programming sometimes apply. Okay? General graphs, there is no left to right order among the edges. In your bandwidth problem, there's no left to rightness in the graph. Okay? So it's probably not something that's going to apply. But anyway, it's a general technique for solving optimization problems. And the one algorithm that you have seen so far that fell into that category was Floyd's algorithm. Floyd's algorithm, which for all pairs shortest paths, there was a recursive formula, okay? And it built up examples from smaller examples. Any questions? But we're going to start today from a very, very simple problem, okay, on dynamic programming, so people really understand kind of what the idea is. Okay, any questions? First, a little philosophy of what we are going to be doing, okay, how this fits in with everything we have done. We saw that there are greedy algorithms, okay, where you try to make at each step the best local choice, okay? Which is the best way for me to go next on a shortest path tour, okay, or a traveling salesman tour or something like that. And you kind of may hope that the ultimate global right thing to do is determined by the best thing to do from this small example, making it bigger, okay? Sometimes that works. That's worked on minimum spanning tree. But in general, a greedy solution where you are making local decisions, only locally, okay, will probably not give you the best. Local decision isn't necessarily the best global decision, okay? Now, what we would sometimes like to do things like we're doing in this particular assignment, go through backtracking and search through all possibilities. That way will give us the best possible solution for something. But it requires searching through an exponential number of possibilities. Dynamic programming is going to kind of occupy a middle ground between here. We're going to design algorithms which systematically search all possibilities. So correctness is not going to be an issue, okay? Any more that correctness is an issue with these backtracking things. How are you going to know your backtracking program is right? Well, I searched all permutations. What else could it have been? Okay? Dynamic programming, we're going to systematically search through all possibilities. But for certain problems, we can use store partial results to avoid recomputing them. And if we are lucky, the partial results will not only make it a little bit faster, the way pruning might do with backtracking, but can provide a big O improvement in efficiency. Okay? Any questions about that? This is still nebulous philosophical material. We'll get a little more concrete in a minute. Any questions? Kabunk. So, the algorithms that we're going to be basing our dynamic programmings on are going to be recursive algorithms. Okay? And usually the recursive algorithms are going to be described by a recursive formula, okay, which you may know of as a recurrence relation. How many of you have taken AMS 301? Okay, did you talk about recurrence relations in there? You solve all of these things, so you should be familiar with recurrence relations. Recurrence relations are formulas that define things in terms of themselves. Okay, and they are interesting mathematical representation of things. The recurrence relation an equals an minus 1 plus 1 says that the nth term of our sequence is going to be the n minus first term of the sequence plus 1. And when you take a recursive formula and you start it with initialize it with a base case, you get a sequence of numbers. If we start out with the sequence of 1, and then take the next term as 1 plus the previous term, 1, 2, 3, 4, we get this recursive formula computes the sequence A of n equals n. Any questions about that? Do people see why that is? A sub n equals n for this? Any questions? Like, I don't understand is a good question. Okay, what's a recurrence relation? It's a good question. So what's interesting about recurrence relations is that they are naturally express all kinds of different functions. An amazing number of natural functions are easily and concisely represented by recurrence relations. Any polynomial, you're used to polynomials like an equals 4n to the 6th plus 3n cubed plus 1. This can be defined by a recurrence relation. Any exponential function, like a to the n equals 2 to the n. A sub n, the nth term of of our sequence A is 2 to the n. That can be naturally defined by a recurrence relation. Look at the recurrence relation. Each term is twice the previous term. If you start out with 2, what's twice 2 is 4. What's twice 4? It's 8, 16, 32, 64, ... right? So you can encode exponentials with recurrence relations. Recurrence relations are also powerful enough to encode a lot of other weird functions. And some functions that you may already know about are weirder than you think they are. Obviously, everybody here knows about what n factorial is. But it's kind of a weird function. That's why they had to assign it. They say, what's so weird about it? Note that the notation, the only reason you know about n factorial is because they gave the exclamation point to it. Okay? What is 2.5 factorial? 2 factorial, everybody knows, right? Well, 3 factorial is 6, right? 4 factorial is 24. What is 2.5 factorial? Okay, does anybody know? Yeah? Gets complicated because factorial is a weird function. It's only defined on the integers. Okay. So there are generalizations to try to compensate, to talk about weirder things about it. But recognize that it's weird. Everything else you learned about in polynomials and exponentials didn't have this constraint, right? But factorials arise because there is a natural recurrence relation for them. The nth term of the factorial sequence is n times the n minus first term, right? And this recurs. You start with 1. A of 2 is 2 times 1, or 2. A of 3 is 3 times A of 2, or 6. A of 4 is 4 times A of 3. Relations. When we think about recurrence relations, we're not going to solve them algebraically like you might have done in AMS 301. We're going to solve them by evaluating them, by basically thinking about what gets executed, writing a computer program to solve that recurrence. Any questions? Again, I don't think people are still, this may be still a little nebulous, a little bit philosophical. Any questions? Let's now look at a recurrence relation that you guys have seen and that you have tried to compute, and let's think how we compute it. The Fibonacci numbers, okay, are the numbers governed by a recurrence relation. Said the nth Fibonacci number is the sum of the 2 previous Fibonacci numbers. F sub n is f sub n minus 1 plus f of n minus 2. That is the Fibonacci numbers. Does anybody know why people care about Fibonacci numbers? What? Heard golden ratio, but that's that square root of 5 thing I was mumbling about. Okay? You're saying that there's some connection here to rectangles and stuff like that. Okay? Maybe. Okay? Any other reason we care about Fibonacci numbers? What? Fractals, you say, well, they sort of come up. Why is it that why did Fibonacci originally talk about this formula? Does anybody know? Yeah? Right, he was trying to figure out how many rabbits you get if you leave them alone for a while. Let's say at time 1 you have 1 rabbit. And let's say rabbits breed in their second year. Okay? After 2 years you have 1 rabbit and nobody got born this year, so you still had 1 rabbit. The next year, the rabbits that you had bred, and so you had the previous 2 years ago's rabbits plus the new ones you create. They basically came up with it as a model of rabbit growth. Okay? Wasn't really a great model of rapid growth. But why does it occur in a lot of things? You were saying fractals, you were saying golden ratios. The real reason it occurs is because this is about the simplest recurrence relation you can come up with. Okay? And some simple mathematical formula probably comes up in a lot of different things. That's, I guess, the philosophical reason as to why Fibonacci numbers come up a lot. It is about the simplest recurrence relation you can come up with. Okay? And so if anything can be modeled by recurrence relations, Fibonacci numbers can. Any questions? Actually, none of that is still yet very helpful. But how would you write a program to compute what the nth Fibonacci number is? Okay? Suppose you wanted to write a program to compute the nth Fibonacci number. How would you do it? Okay? Yes?
Probably iteratively.
Well, you say iteratively, not iteratively, because right now you've got a recursive thing going on. What would the natural Fibonacci program go? Okay, yeah? Does everybody see that we would write a program that went something like fib sub n would be if n equals 0, print 0. If n equals 1, print 1. Otherwise, print fib sub n minus 1 plus fib sub n minus 2. Can people, I know you can't read what I wrote, but do people understand what I wrote? Does people see this as a recursive program? Okay? Has anybody ever written a recursive Fibonacci program before? Most people, right? It is easy to write this program. What is the running time of this program, however? Okay? Yeah?
It's exponential on the order of n.
It is exponential in n. And let's go through this. This is important to see. This innocent looking, okay, recursive formula yields an exponential algorithm. Why is it an exponential algorithm? When you call it on fib sub 6, what is it going to do? It is going to go call fib sub 5 recursively. And in order to compute fib sub 5, it's going to go compute fib sub 4. To compute fib sub 4, it's going to call fib of 3, fib of 2. Fib of 2, ka-chunk, ka-chunk, ka-chunk. Fib of 2 equals 1, right? Fib of 3 is going to be 1 plus 0. 1. Fib of this 3 is going to be 2. In order to finish computing fib 4 when it backs up, it starts to compute fib 2. And here is where we get into trouble. Because it is going to compute this thing again. Does everybody see that? If we just have this recursive program, it is going to compute fib sub 2 again because it computed that. But that was returned from a function call. We called the function again. So fine, it's going to go compute this thing and this thing again. And fib sub 2 is again going to come out to be 1. And so fib of of 4 is going to be 3. Now, in order to compute fib of 5 is going to be fib of 3. In order to compute fib of 3, we've got to compute this whole thing again. Okay, does everybody see that? And by doing the naive recursive thing, we are recomputing this whole big branch again. And it's going to get worse over here. This whole branch here of computation, fib of 4, we already computed over here. Does everybody see that with the recursive implementation, the way it is, we are recomputing the same thing over and over again? Any questions about that? Now, how much work is actually being done here? Okay, we say it's exponential. Let's think why that really, can we really argue that it's exponential? The way I would argue it is the following. In fact, when you took AMS 301, you learned that the nth Fibonacci number is something like the golden ratio to the n, which is something like 1.6 to the n. Where did that stuff come from? Well, in order to get a number that big, each one of these nodes, the value of that number is simply the sum of all the leaves below it. Each leaf is either going to be a 0 or a 1. In order to get a number as big as 1.6n, by adding up numbers that are either 0 or 1, you'd better have at least 1.6n things that you're doing here. Does everybody see that? We're going to be computing f of 1, 1.6 to the n times. And this is exponential, and this is very exponential. When you run Fibonacci numbers here, by the time if you wrote this recursive program, by the time you got the fib of 50, your program would be out of gas. It'll run and it'll hang. Has anybody ever done that? Have anybody seen that? Yeah. Try. This was the most educational program I ever wrote when I was an undergrad. I couldn't believe it. You know, fib of 50? What's the big deal? But you hit it, and the fib goes gung, gung, gung. Okay? And the reason is because it's exponential. Any questions? But is this the right way to compute the nth Fibonacci number? No, it is not. And the reason is because there is a linear time algorithm, okay, for it, based on storing the results. Okay? If we compute the nth Fibonacci number, the nth Fibonacci number will be trivial to compute if we have the n minus first and the n minus second. What if we really want to compute the nth Fibonacci number? Why don't we compute the first two Fibonacci numbers, okay? Then build an array of Fibonacci numbers by simply repeatedly adding the last two terms that we saw. 0 and 1, 1. 1 and 1, 2. 1 and 3, 3. 5, 8, 13, 21, 34. Does everybody see what I'm doing? 55. Okay? We can evaluate this recurrence relation faster by only evaluating each number once and then looking it up when we need it. Okay? That is the big idea of dynamic programming. Any questions here? Okay? Does everybody see that if we have an array here, f, if we now view f as an array, not as a recursive function, we can compute f of n by filling in the array one element at a time. And the cost of filling in the nth value is simply adding up the two previous terms. Adding up a constant number of terms takes how much time? Constant. We have a total of n things we're computing, each of which takes constant time. The total amount of time to compute the nth Fibonacci number is order n. Any questions about that? Okay. Any questions about this particular example? Okay. It is an example showing how we basically are using more space than before. We had to store these values. but we are willing to store things for the improvement in time. And the improvement in time here is a big deal, going from exponential down to linear. Any questions about that? Okay. Any questions about this particular example? You have to understand this example before we move on to anything else. Okay? Any questions? Okay, good. So why do I like dynamic programming? Again, like I tell you, okay, there are what is dynamic programming? It is a way of efficiently computing recurrence relations by storing partial results. Okay? So, if I can take my problem and describe what I want to compute by a recurrence relation, okay, namely a recursive program, okay, if it is the kind of thing where I'm going to be seeing certain solutions over and over and over again, okay, then I am better off storing partial results than recomputing. Okay, and again, if you look in the book, you'll see there's a lot of war stories here where dynamic programming proved to be the right thing to do. Okay, this is one of these areas where if you really understand it, you can get a lot of mileage from it. Any questions? Okay. But we have just looked at a very, very simple dynamic program for computing, what you call it? Well, let's see, what's the philosophy here? Let's say, again, I've said this enough times already. The key in dynamic programming is that we're going to take a recursive algorithm. If we see that it repeatedly computes the same subproblems over and over, then storing it in a table instead of recomputing will lead to an efficient, effective algorithm. And so, when we think about how we solve problems with dynamic programming, the big thing is to first look for a correct recursive algorithm and then hope that we can speed it up by storing the results. Any questions? Okay, that much is clear. Let's look at another example of dynamic programming in action where we're going to evaluate a recurrence. And it's going to be a slightly more complicated recurrence than you have seen before, than we did before. Fibonacci numbers are the simplest recurrence. Okay? We're going to look at something else that you learned in AMS 301 and probably high school about computing binomial coefficients. How many people here know what a binomial coefficient is? Okay, people don't know. I've never heard that before. Probably heard it, but you're rusty. By the binomial coefficients, I mean n choose k. Okay? It means the binomial coefficient n choose k counts the number of ways you can choose k things out of n. Okay? Does everybody get that idea? So if we wanted to figure out, we have an n-member class. Let's say in this class there's n students. And let's say that you guys don't like what I did on the midterm. You want the midterm canceled. Maybe you're going to try to decide to develop a k-element committee of people to come protest to me, to represent the class. How many different possible committees are there? Well, how many ways are there to form a k-member committee out of n people? Well, that's what we denote by n choose k, the kth binomial coefficient. Any questions about that? Here's another question where binomial coefficients are very useful counting numbers. Suppose you are in Manhattan. Okay, you are in Manhattan and you get into Penn Station. Penn Station is on 7th Avenue and, was it 8th Avenue? 7th Avenue and 33rd Street. Right? And let's say you want to get up to, go over to, let's say 11th, 7th, 8th, 9th, 10th, 11th Avenue and 44th Street. Okay? How many ways are there to walk from this reasonably to walk from here to here in the city. Now note that in the city, you have avenues, for those of you who have not been there, the avenues run north-south, south. The numbered streets run east-west. Manhattan is a grid, okay? And what's nice about a grid is that there are many ways to walk across it, which are of the same length. I mean, one way you could walk from, how many ways are there to walk between here and my office? My office is over there. I would say there's one way to do it if you want the shortest path. Of course, you could take a lot of crazy ways. That's not what I mean. How many shortest ways are there across this grid? Okay? I claim this can be counted by the binomial coefficients. Suppose, let's say, we have a grid which is, let's say, n avenues by m cross streets. How many ways are there to walk across from there to there? Any ideas? Yeah? N plus m. N plus m total? The answer is no. Okay? I mean, the length, any way of walking is going to be of length n plus m. Does everybody agree that I could walk from here to here, go ka-chunk, ka-chunk? That's going to be n plus m. That's the shortest path length, right? But you see that there's lots of ways I could do it. I could go down this for a while, do a ka-chunk, come over, and then do it, right? Or maybe I could walk like this, ka-chunk, ka-chunk, ka-chunk. Does everybody see that? How many ways are there to walk from here to there? Any idea? Yeah?
Well, it's equivalent to the number of ways of rearranging like 11 identical rights with 4 ups.
So you're saying that in this case, if I'm going to be doing it, each time I'm either going to be moving to the right or up. I'm going to be having 4 ups. And he says 11 rights. Right? How many possible sequences can I construct from 4 ups and 11 rights where I end up over there? Okay? How would I do that? How many ways are there of doing that? Well, there's going to be a total of 15 different steps on my trip, right? And 4 of them are going to be ups. My trip is going to be defined by what were the exact positions I did my ups. Here I did an up in the 3rd position, the 5th, 6th, 7th, 8th, 9th, 10th position. Does everybody see that? So if you follow that, the number of ways of doing it are going to be n plus m, choose m. Okay? These are my total number of steps on my trip. Exactly m of them are going to be ups. Anything that is not an up is going to be to the right. The number of ways of doing it is m plus n, choose m. Any question? How many people see that? How many people don't see it? Okay? If you don't see it, talk to your AMS 301 teacher. You should have talked about that day. Any questions? Okay? But it should be clear that counting binomial coefficients is an important thing to do. That much should be clear. How do you compute n choose m, n choose k? Okay? If you had to write a program to compute n choose k, how would you do it? Okay? Let's think about it. There's a natural and wrong way to do it. What is the natural and wrong way to compute n choose k? Somebody, yes? Well, what you want to say is, well, okay, it depends what you but I think what you're saying is there's a formula for it, right? And in fact, the formula is that n choose k is n factorial times n minus k factorial, k factorial. What you're saying is if I want to compute what n choose k is, I could use this formula. Is that correct? Now, what is bad about using this formula to compute n choose k? Yes.
You have to store really big numbers.
You've got to store really big numbers. Okay? How much is 1,000 choose 999? Does anybody know? How many ways are there to choose a 999 element subcommittee? From 1,000 people? Not 2. How many? Yes. 1,000, right? One person's going to be left off the committee, right? How would we go about doing it with this formula? You immediately compute 1,000 factorial. Am I correct? 1,000 factorial is a humongous number. You can't compute that, right? Or without, in a normal arithmetic, without special magic. 100 factorial divided by this thing. You've got to somehow, if you think you're going to compute this thing, the only way you can do it without overflows maybe would be by canceling in the right way. But canceling in the right way is remarkably tricky. This is not how you compute n choose k. Any questions? How do you compute n choose k if you are doing it in a civilized manner? You did it in high school when you computed Pascal's triangle. Does everybody remember Pascal's triangle? What was Pascal's triangle? It was this number thingy that you did where each element, what was the value of this number going to be? It was the number, the sum of the two numbers above it, right? Does everybody remember that about Pascal's triangle? That I think people remember. But why did you do this? Was it just because your teacher was giving you arithmetic practice? Yeah?
It was a way of iteratively computing n choose k?
It is a way of computing, it is a way of computing, okay, binomial coefficients, okay? Basically, each one of these numbers is going to be a binomial coefficient. And we are computing it by adding up smaller numbers. Does everybody see that in the course of doing this? If, in fact, any one of these numbers is a binomial coefficient, Pascal's triangle computed it by adding up smaller numbers. And so we wouldn't have this kind of overflow problem that we would have with the evaluating the closed form solution. Any questions? All this led into it, if I'm confusing everybody, zoned out up till now, this is what Pascal's triangle is doing. Okay? But Pascal's triangle is saying is at the end, the n choose k, the binomial coefficient n choose k, is the sum of two other binomial coefficients, the ones on the previous row, correct? And in fact, if you looked at what this was doing, if we were interested in n choose k, we were summing up each element on the nth row was the sum of two elements on the previous row, the n minus first row. Okay? And in fact, what made binomial coefficient, Pascal's triangle, work was this recurrence relation, this recursive formula that said that n comma k, the number of combinations of that was the number of combinations of n minus 1 elements in k minus 1 committees plus the number of committees formed of k elements out of n minus 1 committees. Okay? Why was this formula right? Okay, actually, as I'm talking to you people, I can tell that I've wandered into details you don't care about. Take a deep breath now, because now is a point where you have to start to pay attention. Okay, everybody, deep breath. Why is it that this recursive formula correctly computes the number of ways of choosing k element subsets from n elements? Does everybody see we've got a recursive formula? To compute this, it depends upon two other values of this recursive formula. Okay, how many people see that? That's just looking at the screen. Any questions here? Why now is this formula right? Can anybody give me an argument as to why this formula, recursively formula, counts the number of ways of making k-element subsets out of n elements? Why is that formula right? Anybody? Okay. My claim is, if I am building a k-element subset out of n elements, I can tell you that every subset like that has one of two properties. Either it contains the element n, or it doesn't. Is there any k-element subset built from elements 1 through n that does not either have n or doesn't have n? No, there's only two possibilities, right? How many, if C choose n choose k, counts how many ways to pick, in general, k-element subsets out of n-element subsets? How many k-element subsets are there from the numbers 1 through n that do not include the number n? Okay? How many k-element subsets can you build from the numbers 1 through n minus 1? How many? N minus 1 choose k. Does everybody see that? This is counting the number of ways of doing it which didn't use n. How many ways are there to do it where you did use n? Okay? You now have to choose the rest of the subset, right? How many ways do we choose the rest of the subset? N minus 1 choose k? No, because you have to fill k slots, one of which is filled. Does everybody see that the rest of the numbers have to come from the numbers 1 to n minus 1, and we want k minus 1 of them? So the reason this formula is working, and this I want you to pay attention to for just another minute, the number of ways of getting k-element subsets out of n is either every subset you separately count the ones that did include the element n, and the numbers that didn't include the elements n. If it did include n, then you've got k minus 1 slots to fill from the numbers 1 through n minus 1. If it didn't include n, well, you've still got to pick from the numbers n, 1 to n minus 1, but you've got to fill all k slots. How many people see why this recurrence relation computes n choose k? Any questions about that? Question like, I don't see why it computes n choose k is a good question. Any questions? Okay. So how can we now use this recurrence relation to efficiently compute the nth binomial n choose k? Okay. Well, when we have a recurrence relation, we need to have basis cases. This is a recursive formula. But what are the stopping conditions if we wrote a recursive program here so it didn't go out to wazoo? Okay? What values of n choose k do we know the answer for? Okay? Yes?
We know the answer to n choose 1.
What is, okay, so you're saying you know n choose 1, and that is what? How many ways are there to pick a what element subset from n things? That's 1. Are there any other cases we know the answer to? Let's think about it. N choose n. How many ways are there to take n people and pick n of them for the committee? What? N factorial? 1. That's a little bit smaller, right? Does everybody agree that that is a base case, right? Is there any simpler base case for this situation? What? N choose 0. How many ways are there of picking n 0 things out of n? Well, 1. Okay? So this is a slightly more base case than this, right? If you look at what's happening in this recurrence relation, sometimes the big number is getting smaller and the smaller number is getting smaller, and you will eventually run out of the bottom term. Sometimes the big number is getting smaller, and you will run out of the big term will match the smaller term. So both of these basis cases can exist. Any questions here? So a recursive formula is you need a formula and you need the basis cases. Any questions about that? Okay. Now that we have the basis case, how can we write a program to compute this? We have a recurrence relation. The recurrence relation is going to get its way by calling itself to generate smaller numbers. In Pascal's triangle, we filled in the numbers, remember, like this. We walked along the triangle, and if we filled in the triangle like this, the two numbers we needed were already computed, right? We computed from the smallest. These were the basis case. Basis case. These were all 1, 1, 1, 1, 1. 1, 1, 1, 1, 1. Right? And we filled in the rest of the triangle. This was the element that we wanted. But to get to this point, we instead filled in the smaller values and kept filling in smaller values. Okay? So that we knew whenever we filled in a value, the two guys we needed were there. This is my program for doing it. What am I going to do? I am going to set up a matrix. Okay? BCIJ is going to be a matrix, n by n matrix, that will, for any value I and for any value j, will tell me what the binomial, what I choose j is. I am going to fill in the case of I0 is one of my basis cases. If you think about my array, if I'm going to be computing, here's n and here's k. The first situation, where k equals 0, that we said was always going to be equal to 1, regardless of what n was equal to, right? The second initialization condition said that whenever j was equal to j, or n choose n, it was equal to 1. Where is this initialization in this matrix? I heard the word diagonal. Is that right? Yes. Ka-chunk, 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 ka-chunk. Okay? These values I'm now going to initialize in my matrix, right? And then how do I go about filling things in? Well, I am now going to have a two-nested loop that says I'm going to fill it in. I'm going to try for the first loop, the outer loop was governing n. I'm going to fill in the nth row of this thing by walking through for every column in there. So in general, okay, I'm going to fill this thing in like this, like this, like this. Okay? I'm going to iterate through for n. This was really choosing my n value. For k goes from 1 to this thing. N choose k is going to be the sum of two terms on the n minus first thing. And those are the ones that are in a leftmost column. The column just to the left of the one that I'm filling in. Does everybody see that? And because those numbers are sitting there, I can in fact compute this thing by just adding up those two array elements. Come, get away from me. Good. Does everybody see this? Okay. That I'm going to compute the ij term by summing up the two previous terms, which already existed in my matrix. Any questions about that? How many people see what's going on? I may have been a little long-winded about it, but any questions about it? Okay? If you want to understand it, what are the important points? Well, we have a couple points still to get through it here. But basically, what is the important point? The important point was we formulated our problem as a recurrence relation. We then came up with a table to describe all the possible values of that recurrence relation. N choose k. This number here, anywhere in the tree, was a number from 1 to n. This number here was a value from 1 to k. Therefore, an n by k table would summarize all values. We wanted one of these values. And in order to do that, we had to compute the right 2 values from the one before it, which depended upon the right 3 values from the one before that, the right 4 values. By computing it this way, the values we had were already waiting for us. Any questions about it? What is the running time of this algorithm if I want to compute n choose k? Okay, this is a big point here to think about. What is the running time of this algorithm? Okay, it is going to be the number of cells we fill in times the time it takes to fill in each cell. How many cells in this matrix do we have? Yeah? N squared. Well, okay, in general, I guess n squared. Okay, n squared, or to compute a particular n choose m, n by m in the appropriate subarray. Okay? How much time does it take to compute each element? The place where we compute each element is here. Does everybody see that? What do we do to compute this element? We add up 2 numbers that are already in my array, right? So what is that going to be? How much time does it take to fill in each spot? Constant. So how do you analyze a dynamic programming algorithm? It's the number of array cells you're filling in times the cost to fill in a particular cell. Here we have n times k cells we're filling in. Okay? Okay? Each of which is, or maybe n squared times cells that we're filling in, each of which takes constant time. This is an n squared algorithm. Any questions about that? Okay? Any questions?
You said number of cells filled times the time to fill each cell.
Yes, that's the bottom line of what we're doing. You've got to fill, you're at work. You have to fill up, your job is to dig, 1 million holes. How much time does it take to dig 1 million holes? How much time does it take to dig 1 hole? Times 1 million. Okay, and that is how we analyze these things. Any questions? So, just as, again, to summarize, there are going to be 3 things we're going to do, okay, in general to solve these things. We are going to describe what we want to compute by a recursive formula or a recursive algorithm. We are going to show that although it is recursive, okay, the number of different arguments to your recursive function isn't that large. That's why you can benefit from storing the results, because you're computing the same thing over and over again. Once you count how many boxes there are, okay, and how much time it will take to compute it, if the boxes are already filled in, you know what your efficiency is going to be. And the final thing is to find a way to walk through your matrix such that you fill in the cells so that the ones you need have already been computed before. These are the 3 steps we take. Any questions? Okay, look at this, figure out why the binomial coefficient program worked. If you can do that, you're ahead of the game, and I will see you on Tuesday. Thank you for your attention.